I think every second or the other, someone wants to be admitted.
Yes, sir. Yes, sir. It is going on, sir. It is. We'll wait for a few more minutes, sir, and we'll start.
You are located where in Nagpur?
No, sir. It is near Bombay. In Bombay,
Acha.
Bombay Goa Highway, our university is situated.
Uh-huh.
Nearly 600 acres premises is there, and it is equidistance from Pune and Bombay.
Okay, okay,
From
okay.
either way, it can be reached. 90 kilometers is there, sir. It can be reached.
Right, right, right.
Mrudul, shall we begin?
Yes, sir.
Ha,
We shall.
please.
Yeah. Um, Hello, everyone. Thank you for sticking to the time and moving forward to our last keynote speaker for the day, Professor A.K. Verma, sir. Dr. A.K. Verma, sir, is a professor in engineering at Western Norway University of Applied Science in Hokksund and has been in Norway as a professor since 2012 and was a professor senior scale professor for around 15 years at IIT Bombay with Reliability Engineering Department of Electrical Engineering. He is also a guest professor at Lua University of Technology, Sweden, and has been an adjunct at University in Norway and has been awarded honorary professor at MIT University, India, and is also a also has a lifetime achievement award at IIT Madras by SRESA. He was the director of the International Institute of Information Pune on Lien from IIT Bombay from August 2009 to September 2010. He is the Springer Book Series editor of Reliable and Sustainable Electric Power and Electric System Management, Springer Book Series editor of Assets, Analytics, Performance and Safety Management, and also has the Springer Book Series editor of Fire Safety Engineering and Management, and his recently joined edited the books titled include the following: reliability and risk evaluation of wind integrated power system, reliability modeling and analysis of smart power system, and many more. Uh, he has been a guest editor of special issue of DQM Communications 2006, 2007, and 2009, and special issue on dependability in the computing system of International Journal of Performability Engineering 2006. He was a guest editor of a special issue on reliable computing of International Journal Automation and Computing October 2007, May 2010, with Professor Roy Billington and Professor Rajesh Karki. I'm glad to have such a personality with us today. He has been a patron, general chair, conference chair of many international conferences. Glad to have you, sir. Please start your conference.
Welcome, sir, on behalf of the conference, and I request you to take over the session. Thank you.
Thank you very much, Dr. Brijesh and Mridul. I think she
He's the host.
introduced.
Yes, yes, sir.
Yes.
And thanks to all other people who have supported this conference. I think Professor Milipant
Yeah.
and some others I may forget. So I am indeed grateful for this unique privilege. And of course, this time has been especially December and January, almost every week, I think one conference or the other, I have had this privilege of giving some talk or the other. So it's indeed nice to be here for this conference, of course, digitally, but I think we still connect with so many people, and so that's a great advantage. Now, regarding my talk, the issue is primarily maintenance of engineering plants. You know, we are all aware, I think most of us, that a huge budget on, a huge budget in operation and maintenance, almost 40% of it goes towards maintenance in most engineering plants, complex plants like refineries, petrochemicals, pharmaceuticals, manufacturing plants, and so on. So this is a huge drain on the finances, and where people are struggling for every penny, to improve the bottom line. And for that, they work so extremely hard to make it possible. And then you have systems which are failing, not performing to the expectations, and therefore there are so many different kinds of losses incurred, and ultimately the bottom line is severely impacted. And so the competitive posture of the company in the marketplace is gradually wearing down. Now, those were the days, when maintenance was considered a necessary evil, was a kind of thankless jobs. But those days are gone long back. And nowadays, you have some of the best people entering into the maintenance, because after all, you are trying to prevent systems from failing, and you are trying to, carry out some maintenance which is just in time. You don't want to go in for an overkill, in the sense that you do too much of maintenance than is actually required, and therefore you spend a lot of money on them by using all kinds of technology, condition-based systems, and so on, and using all different kinds of strategies for inspection, testing. So you end up spending a lot of money on maintenance, and that's what exactly you are trying to prevent. Or you don't want to underplay it at the same time. If you underdo it, you end up with many failures, and especially breakdowns, and some of them can result into safety related issues, which can have severe impact on the personnel inside the plant, on the equipments, on the facilities, assets, and maybe the environment and the community outside, and therefore attracting lots of liabilities and violating the laws of the land, violating regulatory norms, and therefore getting into much bigger trouble. And therefore, a lot of now resource and time and research is now focused on trying to understand the nitty-gritty of maintenance and how to optimize it, how to kind of minimize, but but without impacting the availability of the plant. The plant has to be available all the time for production or for process operation, and the reliability. Availability, that means on demand it should be available, on demand it should be there, and the correctness of operation, correctness and continuation of the operation without impacting the safety. So, so that's primarily an issue with maintenance. Nowadays, what has happened is there's a lot of emphasis on trying to use computational intelligence, soft computing into maintenance, because because maintenance world is quite uncertain, with multiple modes of failure, system interdependencies, stochastic interdependencies, and combined with too many uncertainties, and with lack of data, incomplete data, unavailable data. So there are so many uncertainties now moving around the plant that maintenance becomes really difficult. And then trying to do it primarily based on statistical data becomes a problem, because the statistics which is compiled from data which is uncertain, which is not available, which is incomplete, has to be taken with a pinch of salt. And therefore trying to carry out some preventive maintenance, build up a calendar-based maintenance program, which is primarily based on statistics, typically mean time to failure or mean time between failure and so on. So is really a big question, that it's not reliable, it's not effective, and it doesn't serve the purpose. and therefore trying to use all scraps of information which is available, not merely from statistics, but try to collate information which is also available with people who work in the plant, people who are designers, or people who have been running the plant, operators, or people, the maintenance crew. They have a lot of expert information. So how to patch up all this information and make it meaningful as far as the maintenance of the plant is concerned. And you don't want to overdo it, and you don't want to underplay it. So you want to basically carry out just-in-time maintenance. Just before the failure happens, you carry out either a replacement or a repair, so that you have used the system and the plant to its most optimum extent for production and for operation. So, but at the same time, there are certain other complexities, certain systems, for example, offshore oil platform, or or a cruise ship, or a warship, or a transport ship. They are basically there in the sea with minimal resources, very limited resources, and both in terms of people and both in terms of spares and so on. So how would you carry out the maintenance so effectively? Because if it doesn't work out well there, then you incur huge losses. So this idea of e-maintenance platforms, etc., has come up, and that has to be integrated with the design framework of maintenance at the conceptual stage of the engineering plant itself. At the design stage of the engineering plant, it has to be integrated, especially for e-maintenance platforms. So this comprehensive idea of using intelligent resources, and especially for remote locations, to be integrated with the design of the plant, at the conceptual stage itself. Because if you invest there your resources and time and money, then you are going to save a lot of money later on, rather than working on breakdown maintenance, catastrophic failures, and then losing money on operations, losing money on safety, losing money on maintenance, and so on. So this is essentially the topic that we are going to look at, and I'm going to just take you quickly through the points. So use of fuzzy logic in maintenance decision making. I did build up a rationale for trying to use all scraps of information that may be available for optimal maintenance. And the bottom line is that you cannot completely rely on the calendar-based, time-based maintenance, primarily because most of the failures that happen in the plant are not age-related, when it is age related, then you want to basically reset the plant state by carrying out some time-based maintenance. So you can prevent corrosion, you can prevent wear, you can prevent fatigue, and so on. But if there are some kind of catastrophic failures, which come up primarily because of sudden accumulation of mechanical stresses, thermal stresses, electrical stresses, and certain uncertain situations, those still cannot be handled by time-based maintenance. So the thing is that if you can detect a failure sometime in advance, and then try to track it, trend it, and see when the failure is going to happen. It can be in terms of days or hours or weeks, and you can carry out some maintenance just before the failure happens. So you basically need to be able to do a condition-based maintenance, not a time-based maintenance. So based on the condition of the system, how it is changing its state from one state to another, you track the metrics, you track, for example, pressure, flow, temperature, vibration, current, and so on. So you train these parameters, and when they cross certain thresholds, if you project it, and that from the predictive analytics that it's going to fail at some time, and then just before that, you carry out some maintenance. So based on the condition of the equipment, based on the condition of the plant. And therefore, you have a monitoring system, trying to monitor all kinds of parameters, machinery health monitoring system. But again, the metrics, but again, it's important that these monitoring systems performance be quantified, so that you know how well it performs in terms of trying to detect, detectability, and in terms of predictability or prognostic ability to be able to tell the ultimate time of failure. So with these metrics or the machinery health monitoring system, you basically integrate it into the design so that you have taken care of it very early in the stage, in the life cycle of the system. So we are going to discuss this a little later. Quantification of metrics, it's important because ultimately you are trying to relate it to corporate objectives. Corporate objectives are reliability, availability, cost. The plant should be available for production or for operation. And it should, once it begins to operate, it should continue operation. And then it should do it very cost effectively. So unless and until it is possible to integrate it with the corporate objectives, the maintenance objectives should be integrated with the corporate objectives for the realization of the corporate objectives. And then to be able to, do a multi-objective optimization, so that what are these metrics which would correspond to maximum availability or maximum reliability, minimum breakdown maintenance, minimum cost, and so on. So once you have been able to identify the matrix, and then you have some way of trying to figure out the metrics of various systems, and therefore you know which system to deploy, condition-based monitoring system to deploy. So some example by way of case study and then conclusions. Now, the problems with conventional preventive maintenance practice, as I mentioned to you, decision based on statistical measures, dependence on data, possibility of maintenance-induced errors, when it's not needed and you are carrying out maintenance. So while carrying out maintenance itself, you introduce errors. So you are trying to minimize the need for maintenance, and you are trying to, at the same time, increasing the possibility of maintenance. Then in spite of this maintenance that you carry out, the in-service failures cannot be ruled out. Systems can fail before and after. And likelihood of over-maintenance is always there. And when you do a likelihood of over-maintenance, you introduce maintenance errors, or you introduce infant mortality because something has been repaired and replaced. And therefore, there can be some early failures in addition to random failures. Calendar-based actions, not all failures are age-related. And as I said, random failures are not age-related. John Mowbray, in his famous book on reliability-centered maintenance, lists out 6 different kinds of bathtub curve, and then he mentions, 4 different cases in which, out of the 4 different cases, in which everything is not related to wear, fatigue, corrosion, and so on. And therefore, it's not age-related. Therefore, failures can primarily happen due to random events as well. So avoid unnecessary maintenance. How much is right maintenance? What's right time for maintenance? And you don't want to overkill it and underplay it, and therefore just in time. And just in time also, that when the ultimate failures can happen, that you need to know very well in advance, because you need to be ready with the logistics, the spare parts, the crew, the resources, the workforce. Everything has to be sorted out before the maintenance is carried out. And therefore, to be able to get the prognostics right well ahead, so that you can deploy the resources. So quantum of maintenance, time of maintenance, readiness for maintenance is an important issue. Now, the first paradigm shift happened is from scheduled or planned preventive maintenance on statistical measures to observed system condition. If it demands, carry out a maintenance. If it doesn't demand, why do you need to carry out a maintenance? because systems fail also due to over maintenance. When maintenance is not required, you open up the nuts and you do every single thing, alignment, and it gradually becomes misaligned, and therefore there are some failures happening because because it was not needed and you carried out, and therefore there is some error, some slippage somewhere, and therefore the maintenance has increased. So you were trying to cut it down, and as a result of all the things that you did, the maintenance requirement has gone up. Now, condition-based predictive maintenance based on random failures, deterioration failures that show telltale signs. Of course, the assumption is that the deteriorations that happen, shows signs that some parameters are changing. For example, pressure, temperature, flow, or vibration, or misalignment, whatever, or even corrosion, fatigue, where some of these parameters are changing and you can track them. So when you can track them and when you can detect them, then it has to be based on the condition. And then those parameters, it should be possible to track them and it should be able to detect them. So you have early detection, the potential failure, and then the point at which you can detect it, and the point at which it fails, with respect to the age, and therefore you have a warning interval, and therefore there is good lead time so that you can prepare for the logistics, and that you are able to carry out the maintenance at the opportune time. Now, of course, this statistics is a little old, but 2.4 billion US dollars is the global condition monitoring market. So this move from statistics-based, calendar time-based preventive maintenance to condition-based maintenance has now been growing worldwide, and there is increased investment. So $2.5 billion, more than that, is now typically the market. And the survey of effectiveness, but what is the disturbing point is hardly 3% of these companies achieved a measurable return on investment. This is all based on technology, and it becomes really expensive, and therefore you don't achieve the ROI, it becomes a real problem. Now, but it has been, from all kinds of analysis and surveys, it has been brought out that for medium scale industries, typically it could be the return on investment can be ramped up to 60%, and even for large scale industries, large and medium scale industries, it can be even larger than 60%. So there is a lot of scope there. Now, there is a low ROI of machinery health monitoring equipment, is primarily because there is lack of systems approach, inadequate performance characterization, and inappropriate application and poor utilization. The average utilization is only 30%. And I'll tell you something about the lack of systems approach and inadequate performance characterization. Now, the objective is to minimize the catastrophic failures, maximize the ROI. Now, as on today, there is a lot of sophisticated equipment and instruments which can carry out signal acquisition, processing. They are largely confined to standalone condition monitoring tools and equipment, never for the system as a whole. And the coverage, the diagnostic coverage is available only for separate and sub-assemblies, not for the system. And then ultimately at the system level, there is no corroboration of diverse signals. And therefore, there is no possibility of integration of condition monitoring signals at system level and therefore there is nothing which tells you about the performance of the system, especially in terms of prognostics and how long the system will continue before it fails, and when can we start the repair or replacement or whatever. Quality signals from sophisticated equipment is available, but limited information largely about subsystem condition, and very low accuracy of diagnosis and prognosis. Prognosis, to be able to tell well in time what is the ultimate, when is the ultimate failure going to happen, and then be able to detect, diagnose what's wrong with it. So low accuracy, high investment on equipment and expertise. These guys don't come cheap, because they have to be trained in the latest equipment, technology, and to be able to use it effectively. So the experts, the people, the engineers, the technicians, they are with this kind of background would be very expensive for the company. But low returns in terms of system level availability. So you know what the subsystems are doing and how it's moving in terms of their performance, but at the system level, you have very little idea about its performance, and very low returns. For example, for a diesel generator combustion engine, from the exhaust analysis, you can make out about it. And then from the oil analysis about the engine, and then about the motor health, vibration analysis about the shaft, and then performance analysis. But you cannot really infer anything about the diesel generator, the complete system. And you know everything in parts at subsystem or assembly level, but you cannot predict anything about the performance of the system as a whole. And so the inference is not there in terms of its availability. A range of sophisticated equipment is available. Do use of such equipment alone guarantee the effectiveness? No. So the second paradigm shift is from standalone condition monitoring coverage for individual separate entities of large engine plants to holistic and systems approach for large engine plants. So that's the kind of shift that has now happened. So this is the second paradigm shift. Now, for this, to bridge the gaps is very important. You have the maintenance objectives in terms of reliability, availability, corporate objectives in terms of reliability, availability, cost. And the maintenance objectives, the maintenance objectives are in terms of detectability, diagnostics, the prognostics, and then the logistics, readiness, So these are the maintenance objectives. And the maintenance objectives have to be aligned with the corporate objectives. How do these contribute to the corporate objectives? Then, the research in trying to optimize the reliability, the availability, minimize the cost, minimize the breakdown maintenance, and so on. So how do these maintenance objectives ultimately optimize? And what are the kinds of tools and what kind of parameters have to be tracked and trended, and therefore the required education and training of maintenance decision makers. There are multiple stakeholders, and some of these objectives can be conflicting. For example, you want high availability and low cost, minimize the minimum cost. So they have conflicting stakeholder requirements, and therefore, but everything has to fall in place. And then the policy for upgrades. So you have the maintenance objectives, which should serve the corporate objectives, the sophisticated equipment and advanced tools that are required, and the modern research in trying to optimize the resources that are required to be able to meet the corporate objectives, and the effectiveness evaluation, because you spend so much of money, resources on the condition-based predictive maintenance. So there has to be some metric which should connect with the performance, and that should connect with the maintenance objectives, and therefore with the corporate objectives. And obviously the education and training that is required to sustain this. So design condition monitoring system for the plant as a whole, be able to use all available inputs, make significant improvements in plant reliability, availability, and cost reduction. So that's the corporate objective. And you don't want duplications and dissonance. So systems approach, that's the so that's what is required. So the inputs are essentially resources, expertise, information, in terms of the performance of the condition-based predictive maintenance system, to be able to use the condition-based systems, the technology, the resources, the manpower, the finances, etc. So if you so this is what is the input for maintenance system, and the outputs basically relate to the corporate objectives in reliability, availability, and cost. An integration system requires top-down system design, so it has to start from the top down, not from component right up to the system, but from the system down to the component. So the framework is condition monitoring systems requirement definition, the physical plant hierarchy with the failure location, physical disposition of sensors, the failure modes of assemblies, sub-assemblies, components, and therefore the location, and therefore the kind of sensors that have to be deployed in those locations, and selection of condition monitoring devices for fault signal acquisition, integration of sensor outputs, evaluation of detectability and prognostic ability, and then to be able to connect it back with the corporate objectives through a multi-objective optimization of plant performance, because the corporate objectives have to be met, but at minimum cost. The bottom line is that at minimum cost, but the objectives have to be met. Now, a physical plant hierarchy, for example, the plant, is constituted of systems, then subsystems and assemblies, sub-assemblies, sub-sub-assemblies, and down to the component level. Now, for example, a captive power plant may have 3 different modules, diesel generator sets, then each of them constitute of these subsystems like diesel engine, generator, cooling water system, and the cooling water system, which is critical, for example, can consist of water cooler, raw water pump, which consists of raw water pump, consists of motor, pump, then pump consists of casing, rotor, and then the rotor consists of bearings, pump shaft, impeller, seal. So from the system level down to the component level. So to be able to relate it to the availability and reliability, of course, if you have some background in reliability engineering, you know what a fault tree is about, and therefore you are trying to relate basically events that can happen in terms of the failure modes and causes at the component or sub-assembly level to the top event, captive power failure. So you are basically trying to connect something to the reliability and availability in terms of trying to understand failures which are happening at various levels in terms of the various modes to the top event, which is what you are trying to prevent by deploying a condition-based monitoring system. So at the down to the component level, where you have the fault location, bearing failure, seal failure, shaft failure, then these failures happen primarily in different modes. So it could be misalignment, crack growth, bearing seizure, fouling of impeller, material failure, and then, for example, bearing seizure in terms of the causes for these various failure modes, the mechanisms, so to say, the lubrication, overheating, aging, pitting, misalignment, bearing material failure, and of course, associated with the causes are the symptoms. You have, for example, the lubrication failure in terms of lube oil flow, lube oil level, lubrication oil pressure, temperature, shock pulse, vibration, caustic emission. So these are the failure symptoms, and associated with the symptoms, then you come up with the sensors. So you have the failure modes, the parameters to be sensed, and the fault location. And for each of them, we just saw them, lube, oil flow, oil level, and like that, you have like that you have for all of them, for misalignment, crack growth, fouling, and then you come to shaft failure. So like that for bearing failure, casing wear down, and therefore it would connect right up to the top event. And so you have this whole lot of sensors associated with the various failure modes and causes and the parameters and the locations at the point at which the components are exposed to failure. So you have this complete matrix, of sensors which have to be deployed. So locating sensors near component failures, and then selection of sensor types, to be able to select them on certain basis, availability of technology, supportability, redundancy, cost effectiveness. So we can move further. Now, the aim of this presentation is to build up a framework for the machinery health monitoring system selection optimization. You do not want to recklessly get all these sensors and then deploy them and then not be able to achieve the maintenance objective and the corporate objectives. So you want to use them for a certain purpose to be able to minimize the cost and minimize the breakdown, maximize the availability. So you want basically to characterize the performance of these systems so that they relate to the corporate objectives. And as I had told you about issues which relate to data, so you can use all kinds of data which is available. There are people who have been working in the plant for 20 years, 30 years. They are operators, they are engineers, they are designers, they are maintenance crew, and so on. So they have a whole lot of information. So we use these information and to be able to collate them in the form of an expert opinion into the framework for the machinery health monitoring system selection. Now, the performance metrics, primarily detectability, to be able to detect that failure has set in. Of course, it has to be effective and accurate. Accurate in the sense of correctness, and then effective in terms of being able to detect whether some failure has set in. So true positive or false positive, that means there is a actual condition, and then there is what is indicated by the condition-based monitoring system. So if the actual condition relates to the condition which is indicated by the condition-based predictive maintenance system, then it is effective, true positive, and it could be true negative, as it could be false positive also. That means the actual condition is negative, but the condition-based monitoring system indicates that there is a problem, but where it is not. But the effectiveness relates to the detectability in terms of being able to detect whether it's even if it is a false alarm, but it should be able to detect it. And the accuracy is obviously in terms of correctness. Then prognostic ability, first of all, it should be able to diagnose what's wrong with it, and then be able to predict very well in advance with minimum forecasting error with minimum forecasting error with a certain lead time, when is the ultimate time to failure. So the prognostic ability, these are the two characteristic features. And of course, statistically, they can be arrived at, but that's a long and lengthy discussion. So I'm going to quickly move over to the approach that we intend to take. So detectability is a feature which is a weighted sum of effectiveness and accuracy. Likewise, the predictability, the diagnostic ability, these are based primarily on statistics. The prognostic ability of the machinery health monitoring system can be represented as a weighted sum of predictability and diagnostic ability. Now, for our purposes, we don't take this statistical route, but we basically use what is known as the receiver operating characteristic. So we'll get into the details of it subsequently. So the quantification, the statistical approach is a problem, and therefore we cannot take the truth. But information from the experts is available. So we take this fuzzy receiver operating characteristic as an alternate approach, and alternately define the performance metrics, and therefore the fuzzy logic-based quantification of these performance metrics. So the receiver operating characteristic I was telling you about, the condition monitoring indication, it says positive, that means there is a fault, and the actual state says positive, so that's true positive, and the actual state is negative. That means the condition monitoring is indicating that there is a fault, but the actual state is negative. So that's false positive. That's false alarm. So when you say effectiveness, it basically relates to true positive and false positive. It should indicate that there is a problem, but it should be able to detect that there is a problem. But whether it could be a false alarm or whether it's true positive is not the issue as far as the effectiveness is concerned. And therefore, effectiveness is a measure of the performance represented by the ratio of positive affirmations. That means true positive and false positive by the system to the sum of all positive and negative test results. So that's a positive detection probability. Now, when it comes to accuracy, it's basically, whether your detection is correct or not. So it should be related to the true positive and true negative. Okay, so accuracy is all about correctness, correct affirmations. Now, detection, positive detection probability and the false alarm probability, those two things that we saw, the effectiveness and the accuracy, the two together, you can have a rule-based fuzzy inference system to be able to then characterize the detectability and then do a defuzzification to be able to quantify the metrics of detectability. Likewise, for predictability, you have forecasting error. Forecasting error, you have indicated that this would be the time to failure, but actually, the actual time to failure is different, and it's vastly different. So there's a forecast error. And then how well are you able to predict it very well in time? Because when you want to predict when the failure is going to happen, you also should have enough time with you to be able to mobilize the resources, the lead time available with you to mobilize the resources so that you are able to carry out a maintenance just in time. So the forecast error, minimum forecast error, enough lead time for high predictability. And then, of course, it obviously implies that the diagnosis has been correct, from the detectability. So high diagnostic ability, high lead time, and minimum forecast error for high prognostic ability. So we have these rules, and then therefore you are able to characterize the prognostic ability and then characterize it as a metric, and then in this case defuzzify and would give you a crisp value. Let's take a small example. A large power plant, for example, with several subsystem assemblies. The plant is organized into modules based on maintainability factors. For example, air conditioning system, the diesel generator system, the power plant, and the air conditioning that is required. So they form two modules, and then you can have multiple modules in a plant. The aim of the proposed condition monitoring system would be to provide comprehensive coverage of plant health, identify the optimal condition monitoring system for maximizing plant availability and minimizing the cost of condition-based predictive maintenance. Therefore, a typical example would be, which we are going to just broadly see. The steps are primarily preliminary design, of the condition-based predictive maintenance system, modeling of the plant under condition-based predictive maintenance, formulation of objective functions, multi-objective optimization, decision support from optimization results. So determine the physical hierarchy, what are the preliminary design, what is the preliminary design of the system, determine the physical hierarchy, the plant fault tree as we have seen, shortlist set of condition monitoring devices to be installed, integrate the sensors to derive tangible information regarding plant condition and balanced life prediction, generate values for detectability and prognostic ability. So example, under this system, you have a module, for example, the diesel generator module or the air conditioning plant under condition-based predictive maintenance. So is the condition within the threshold? If it is not, then you increase the rate of condition monitoring, and then you check the condition if it is under threshold. If it is not, then add some prognostic features to it, and then check the condition-based monitoring condition of the system, and then decide on the required level of maintenance. So different levels of maintenance, some could be replacement, some could be repair or overhaul. So obviously associated with this is the logistic delay. And if this cannot be done, ultimately it would lead to a catastrophic failure, which would require corrective maintenance with huge logistic delays, which in some sense which defeats the purpose of deploying this condition-based predictive maintenance system by increasing the costs, the downtime costs and repair costs and so on. So identification of the optimal system, you have the field collection and data, some statistical information which is well standardized already. Like that you can always use. And what is available from the experts, by way of fuzzy logic based estimation of detectability and prognostic ability. So that finds its place into the multi-objective optimization, for example, using the genetic algorithm, and then analysis of various optimal solutions which can be present to the stakeholders, to the decision maker as a decision support selection for required solution. And therefore, then accordingly identify the optimal machinery health monitoring system. So we want to factor this, this gets factored into the corporate objectives. So ultimately it would have to be connected, related to the reliability, availability. Therefore we use a Markov model for that, state space, continuous time model, and different states of the system, different transition rates from one state of the system to another state of the system. And I can tell you something about the states of the system and the transition rates. You can have a breakdown state, you can have an inspection state, and you can have a state of condition monitoring with increased prognostic features, and then logistic delay states, and so on. So then, of course, the transition from one state to another with basic condition monitoring features, and then rate of transition to an operational state with advanced condition monitoring techniques to states of catastrophic failure. So you have these transition rates and you have states of the system. And therefore, you can connect the unavailability of the plant to those features of the condition monitoring system through this solution of the state space continuous time model. So you can figure out the unavailability of the plant, which obviously relates to the catastrophic failures and the downtimes, the delays, and then the cost of the condition-based predictive maintenance system, because it has been a source of worry because it's so expensive. So it connects with various condition-based predictive maintenance performance metrics in terms of detectability and prognostics and the logistic rate and so on. And the ratio of the sum of the probabilities of condition monitoring, corrective maintenance to the total maintenance. This is also what you want to minimize. You want to minimize the unavailability, minimize the ratio of corrective maintenance to the total maintenance, and minimize the cost. So you have a whole lot of minimizations to happen. So minimize unavailability, cost of condition-based predictive maintenance, the corrective maintenance to the total maintenance. So you have these two modules, diesel generator set and the AC plant. So machinery health monitoring cover is to be provided for the plant to prevent chances of catastrophic failure. You do anything, but you have to prevent the catastrophic failures because they turn out to be very expensive. So but the machinery health monitoring system has to be cost effective. The efficacy of the proposed health monitoring system is to be assessed prior to implementation. So let's say the parameters of the model, the air conditioning set, the diesel generating set, then you have the cost, the actual cost with the minimum, that ratio. So for detection, prognostics, logistic rate for failures, and of course some statistical parameters as well. Now from the experts, this information has been collated. For example, the periodic measurement of overall vibration levels using handheld meter, daily manual inspection, the detectability and the prognostic ability. So this is the detectability and prognostic ability quantified. So you have automatic performance monitoring, what is detectability and prognostic ability corresponding to that. Then you have overall vibration monitoring, continuous manning of equipment, and so on. Then you have, of course, online performance, oil quality, network e-maintenance, compatible diagnostic and prognostic systems with high values of detectability and prognostic ability. So trying to minimize them, these are the decision variables which factor into the corporate objectives that continuous time, state space, Markov models that we saw, which makes it possible to evaluate the unavailability and other issues. Yeah. So the unavailability, cost of the condition-based predictive maintenance system, the ratio of the corrective maintenance to the total maintenance. Then we use genetic algorithms, So we get, for example, Pareto optimal front with 120 solutions, for example, in the objective space. Corresponding to each solution, there is a set of decision variables, detectability, prognostic ability, and logistic rate. So you have these availabilities. As you can see, the availability increases, the cost also increases. These are the solutions that we have from the Pareto optimal front. So availability versus cost. So when you have higher availability, that's primarily you want more, a better prognostic ability and better detectability, and therefore it's going to cost. Yeah. So likewise, you have ratio of corrective maintenance to the total maintenance and the relative cost. So you have to be able to diagnose and detect the failures that can happen well in advance to be able to reduce the ratio of corrective maintenance to the total maintenance. So if that ratio is going to be small, it's going to cost. So as I said, there are competing stakeholders' objectives, and that yet we would want to minimize these. So this is the 3D scatter plot of cost. So you can see in a box, the ratio, the cost, and the unavailability. So this can be presented to the stakeholders for taking the right kinds of decisions. And then the contour plot. If you are looking, for example, for an availability of 60% or more, then the prognostic features that you require for the modules. For example, the power generation module as well as the air conditioning plant. So you have now these characteristics of the condition-based predictive maintenance system connected with the corporate objectives of availability and so on. So what kind of features you would have to deploy, or you would have to integrate with the engineering system to be able to achieve these corporate objectives. So the options could finally turn out to be something like this, that there are two options. One is the availability of 65%, 60%, the cost, the ratio, of corrective maintenance to total maintenance, the prognostic ability, option one, option two, average detectability, and the broad specifications of the machinery health monitoring system for the module: online performance, oil quality and vibration monitoring, trending, network DE maintenance. So that would go with detectability of 90% and prognostic ability of 84%. And of course, the logistic rate. And then the second option, and of course, you have the cost as well. So this is going to cost a fortune. These all cost units. So 10,000, and whereas the other is going to cost 6,400 multiplied by some unit values, and therefore the amount that you would end up spending to get an availability of 65% and to get an availability of 60%, and the prognostic features that would comply with this. So in conclusion, we have a framework for selecting the optimal machinery health monitoring system strategy. This framework is intended to facilitate conceptual design. This is to be integrated into a machinery platform of large engineering systems to enable e-maintenance. CBPM has been modeled as a multi-objective optimization model based on continuous time Markov process. The three objectives that have been simultaneously optimized using genetic algorithm is unavailability, cost of condition-based predictive maintenance, ratio of corrective maintenance to total maintenance. Then these metrics, detectability and prognostic ability, have been proposed as desirable features to characterize the condition-based predictive maintenance system. And then we have used the fuzzy logic tools for the quantification of these metrics and render them usable in maintenance decision models. And the maintenance decision maker can select suitable strategies recommended for large-scale maintenance infrastructure, such as e-maintenance platforms. So now, well, this is in summary of a book which has been published. This work primarily relates to one of my students' work, Dr. P.G. Ramesh, and we published a book on optimal maintenance of large engineering systems, which is still, I would say, a kind of way ahead in terms of the technology, that is contemporary. In many ways, it's way ahead and provides directions in which the maintenance strategies and the kind of deployment of these computational intelligence tools and techniques are being deployed in trying to conduct, very effective predictive maintenance systems by trying to characterize these systems so that they can be integrated at the conceptual stage, at the design stage of those engineering plants to enable it for e-maintenance platforms. So thank you so much.
Thank you, sir, for your enlightening talk. Certainly, reliability is a major issue in all sort of engineering applications.
Yeah.
Now, I wish to ask among the audience if anything has to be discussed with sir.
So thanks to you and to Professor Milipant, I think,
Yeah.
with whom you have been coordinating,
Madam.
Organizing this event, and
Yes, sir.
For hosting me for this talk.
No, we are also thankful, sir. You agreed very gracefully and immediately you have given the consent, and you were present in time here also and delivered a nice talk. We are really grateful to you. Among the audience, if anyone wish to discuss certain points with sir. Hello, am I audible? Hello?
Yeah, if there is any question, no problem.
Please. Okay, I think they may contact later stage also.
Yeah, sure.
They may contact. Mrudul, please.
Yes, sir. Thank you, sir, for giving your valuable insights in the area of maintenance of engineering plants for e-maintenance platforms. I hope your address would have paved a way to understand the strategies of converging a structural intelligence design framework. On this note, I thank everyone present today and thus declare end of today first day's keynotes and thank you everybody. For the research presentations, kindly join respective break rooms. Thank you.
Thank you very much, sir. We will be in touch with you.
Thank you.
Great.
Thanks a lot.
Great.
Take care.
Yes, sir. Thank you. Have a nice day, sir. Ahead.
Thank you.
Great.
Bye.
Bye.
Stay safe.
Yes, sir. Thanks a lot, sir. Thanks a lot.
Thank you.
Good day. Good
Bye.
day. Sandeep. Hello. Sandeep. You please allocate
Yes, sir.
the participant into break rooms, and let's go with the remaining
Yes, yes.
presentations.
Sir, and me doing.
Yeah.
Yes, sir.
Okay. And those participants who do not have any paper presentation but still they wish to join any break room, you please let Sandeep know. He will accommodate you in the respective break rooms. There is no restriction as such to attend any of the sessions.
Hello, Chetan sir.
Yes sir.
सर अलोकेट करा ना तुम्ही पण तुम्ही पण अलोकेट करा ना
करतोय मी पण करतोय.
म्हणजे
येस.
हॅलो सर. हॅलो.
बोला सर.
सर मी अँटिना सेक्शन मध्ये होतो.
ओके.
आमचे बाकळे रवींद्र.
ओके ठीक आहे करतो.
तर कोणत्या तरी एका सेक्शनला जॉईन करा सर.
अँटिना होते ना तुम्ही. ठीक आहे.
हॅलो.
येस मॅडम.
सर मी नांदेडकर बोलते अँटिना सेक्शन मधून. मला आयओटी सेक्शन मध्ये एंट्री हवी होती.
कुठे मॅडम? अँटिना. एक
आयओटीच्या सेक्शन मध्ये
ओके.
हेलो रविंद्र सर. हेलो. रविंद्र सर.
Hello, Chetan sir.
Yes, madam.
Sir, I am assigned to deep learning and neural network room, but I'm supposed to go at signal and image processing.
ओके, अभी आपको कहाँ पे जाना है फिर? अभी सिंगल
Signal,
इमेज?
हाँ.
ठीक है, ठीक है. तो मैडम आप अनअसाइन में आ नहीं रहे, आप एक बार लॉग आउट करके लॉग इन करेंगे क्या वापस?
लीव करू ना आता?
हा, एकदा लीव करून परत जॉईन करा, कारण
Okay.
अनअसाइन मध्ये येत नाही.
चेतन सर,
यस
सर डीप लर्निंग एंड न्यूरल नेटवर्क के रूम में अलाउ कीजिए सर.
यस यस.
चेतन सर, मी प्रशांत उदान बोलतोय. मला आयपी सेशन मध्ये टाका ना.
हा हा, IoT ना?
आयपी इमेज प्रोसेसिंग.
अच्छा, ओके.
Sir, I'm Shiva Bharati.
यस मैडम.
Sir, please let me in deep learning break room.
यस यस. मैडम आपका भी नाम इधर अनअसाइन में नहीं आ रहा है, आप एक बार लॉग आउट करके वापस लॉग इन करेंगे क्या? क्योंकि नाम यहाँ पे नहीं आ रहा है आपका.
एक मिनट मैं बताता हूँ फिर. हेलो.
हाँ यस सर.
मुझे डीप लर्निंग में असाइन कीजिए और संतोष सर, हाँ डॉक्टर संतोष कुमार, वो संतोष सर और तमीदरासन सर, उनको भी डीप लर्निंग में असाइन कीजिए.
ओके ओके.
सर जिनका हो गया वो लीव कर सकते हैं.
Sir, kindly connect to me in image processing break room.
रमेश.
सर एड मी टू IIT IoT.
ओके ओके. तो आप IoT में है, ऑलरेडी है आप.